And today's speaker is Hennadii Navrotskyi with the talk on writing number of a Gaussian random field along a planar curve. Please, Hennadii.
Yes. Oh. Yes, can you see my screen?
Yes, now we can see it. You can enlarge the slide.
Yes.
Okay, now it's good.
Yeah, so let us begin with a description of the goals of this my talk. So we aim to present some already well-known facts concerning the unit numbers, Gaussian random fields on the plane, and to present some results obtained by the application to a more specific case of Gaussian smooth vector field in the plane. So first, let us reduce the definition of knot on the in the space 3. So the knot in space R3 just caused smooth curve without self-intersections, and two knots are called equivalent if they can be transformed by equivalent or homotopic if they can be transformed to one another by bijective orientation preserving and infinitely differentiable mapping from R3 to R3, which is so-called homotopy. And if the function of a knot does not changes under homotopy, it is called not invariant. Next. So knots can be classified by a minimal number of crossings on their planar projection or planar diagram. So for a knot is an example of a knot. Well, actually, the only knot which with only three with only three crossings on its planar diagram. Otherwise, we need knots because they're used in some polymer models. So the motivation is the following: that polymers are the chain-like molecules that consist of simple, internally simple units called monomers. Since these molecules can be very long, which is they can consist of very large number of monomers, they are often modeled as continuous curves in space RD, and in particular the polymers in random environment are often described as trajectories of a Brownian motion in some space, yes, in the space RD. But there are some problems with this approach, such as that the Brownian motion on the plane has points of self-intersection, unlike the polymer, and also the trajectories of the Brownian motion are non-differentiable with probability 1. So therefore, therefore, Dorogovtsev AA proposed in his 2023 paper on stationary random knot the following construction. So we take a centered stationary Gaussian field on the plane with independent identically distributed components, and the covariance function, which is just equal to e to the power minus u minus v squared. So this Gaussian field is isotropic, and also since the covariance is infinitely differentiable, then it also has infinity differentiable modification. And further, we consider the properties of this infinity differentiable modification. Further, let beta be the image of unit circle in 3 under the mapping psi, and f is some parameterization of beta. So in general, psi can have very complicated shape in the space, well, in the space R3. So next, it was proven in 2023. Yes, by Rogoltsev that with probability 1, our curve beta has no points of intersection with probability 1. So it is indeed a smooth random knot. And also it was proven that for any that with positive probability, beta can be of arbitrary topological type. So then let us define the winding number of the continuous vector field along continuous curve in R2. So it is, in this case, it is just a number of rotation by the vector psi of x when x moves along the curve A. If it is not said otherwise, the winning numbers means the winning number around the origin. So the field psi should not turn to 0 on the curve A. So it is also clear that we can define the winning numbers or any finite interval AB. Same way, it also that the winning number does not change from well, it does not change when we multiply the all vectors by some scalar. The projection of the yes on some planar diagram we can take an yes, planar diagram is just a projection of the knot on some plane. So and we can define overpass, which is just an arc of the knot that goes over one crossing but goes under a crossing. So and the maximum overpass is well, just an overpass which points ends just before under crossing. So the bridge number is just the bridge number of some projection is just the number of overpasses in this projection, and then the bridge number of the knot is just the minimal number of bridges on the set of all of its planar projections. So, for example, on this image, the trefoil knot has 3 bridges, but in general, trefoil knot has bridge number 2, so it can have, so it can be represented as 2 bridge knot on planar diagram. Yes, further, let us explain how bridges and winning numbers and are connected. So it is clear that when we have a bridge, then we have at least one upcrossing by some component of our vector field. So if we have up crossings, then up crossings and down crossings. They're connected to the winning number on the cost planar curve in the following way. So if we have the first component have a finite number of zeros on this curve parameterized by 0, 1, then it is just the number of down crossings of 0 minus a number of up crossings conditioned on the condition on the q of t, which is the second component being positive. Clear? So we can just go here, small image. Yeah, so when our vector fields vectors rotate here, then they cross the point x equal 0 and y greater than 0, and yes, and I greater than 0, and x component is decreasing. So then, and since the winning number on the cost planar curve is always an integer number, then well, we can conclude that it is just equal to the number of up crossings minus number of down crossings. So further, yes. Oh, here vector fields rotates and has rotation 2, winning number 2 on the circle. So further, let us consider some results about the asymptotics of winning number of Gaussian fields, namely of planar. Well, in this case, we'll consider the winning number of two-dimensional Brownian motion. So then the following result was established by Spitzer in 1958 in his paper, Some Theorems for two-dimensional Brownian motion. So it occurs that the winning number has asymptotics when divided by logarithm t equal to alpha distribution, where alpha is some Cauchy distributed random variable. So yes, and this theta of t is connected to the winning number, since clear that theta will change of theta and just equal to our winning number. So further, let us consider the pairwise winning number of of several independent Brownian motions on the plane that start from different points. And it was proved by Yor in 1991. It occurs that they two converge in joint distribution to some set of Cauchy distributed independent random variables. Alpha k, yes, and phi k, these are well pairwise. And yes, we just the winning of one Brownian motion around the trajectory of the other Brownian motion. Then the following result was established by Vasily Kuznetsov, 2015, for family Brownian motion, B epsilon and B epsilon of t. So if we denote x just the rate function for this b epsilon of t, which is just 1/2 of the integral, and then we take the rate function g of a as infimum over a I of x, and let's remind what let us recall what the principle of large deviation means. It means that upper limit lim sub of epsilon logarithm probability that eta epsilon is in f. So let's recall the minus infimum I of x for every closed set f, and correspondingly the lim inf is greater or equal than minus infimum over x over set for every open set. So it is it is said that the eta epsilon satisfies the weak ODP if the first inequality holds only for compact sets from E. Yes, so E is our metric space. Next, then it was proven by Kuznetsov in 2017 that that the family of random products phi epsilon does not satisfy the full large deviations principle on C01, but that it does satisfy the weak large deviation principle on C01 function for the set A of closure of phi minus 1 of A. Just phi minus 1 A. Well, in this case, T на I, 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 where phi minus A, R, C, 1, and R 0 is, well, R of 0 is equal to 1, since we start from the point 1, 0. Then it is cool. Yes, so let us recall what is the goal of our talk. It is to study the winding number of our random field Xi, which was defined previously, along a smooth boundary of some compact set in the space R2. Furthermore, we consider this number as function of set, and then use that it will be a random signed measure in the space R2. So the winding number is also the following index theorem, which allows to calculate the winding number for continuously differentiable vector fields. So then, since the winding number of vector field psi is equal to 0 on the boundary of any domain T, such that psi does not turn to 0 inside T. So then it occurs that we can just calculate many numbers by on small circles centered at points U, which is at zeros of psi. Yes, T. So if And if the matrix of derivatives of psi is non-degenerate in the point u, then we can well have some other simple formula for the calculation of index. So next, there is how to apply index theorem in Hennadii case, which is how to find the expectation of the winning number and the second moment, which is the dispersion of the winning number. And this theorem was also proved by Kuznetsov in 2015. So, and this theorem is a modification of the expectation meta theorem that can be found by Adler and Taylor. Yes, for example, it can be found in the book by Adler and Taylor, Random Fields in Geometry. So the expectation meta theorem allows us to calculate the expectation of u, yes, for t, which is just the number points t such that f t equals u. Yes, and g of t is equal to v. So it's, but we can't apply this theorem directly in our case, because in our case g of t is determinant f prime of t, and the condition for the application of for the application of expectation meta theorem, that the matrix of t f prime of t, prime of t here is also matrix, and they will be linearly independent, but they will are not. So such matrix will be degenerate. Therefore, we can't just apply expectation meta theorem. Well, clear. So then Kuznetsov developed, proved such a theorem. Such conditions are satisfied, for example, by an isotropic Gaussian random field with covariance function, which is infinity differentiable, belongs in a Schwarz space. So in our case, when covariance function is just E power U. Whereas with, well, so belongs to Schwarz space on R2. So therefore we can apply this theorem. Oh yes. So well, and Kuznetsov proved that if the condition it holds, then we can just use Rice's formula. But for such a choice of G, where G is yes, so G is just the signum of where G just the signum, no, G is determinant, and we have indicator. Right, 0 minus indicator G. Yeah, so it is just signum of G of t, where G is the determinant. Number f of t. So we have this representation of the winning number, just the integral of determinant number f of t. Yes. So it is also clear that this well, expectation is well, expectation will be equal to 0. It's here. Equal to 0 for any well satisfying function, and for any f that satisfies our condition a and b. Well, next we recall that our function random function xi was defined as centered stationary Gaussian field with independent identically distributed components. So here we only take two coordinates xi1, xi2. Try to well use our index theorem for them on some random on the boundary of subcompact B. But first we need to prove that there is no points with degenerate derivatives matrix. So no points where xi phi is equal to 0, and determine xi prime of is also equal to 0. So in order to prove it, we just use the approximation of data function h epsilon. So when h epsilon converges to 0, then our expectation converges to some finite value proportional to area of compact B. So, but then let's assume that the contrary well, statement holds. So there exists some random events A of positive probability, such that for O omega, there is some point sign B, such that psi phi is equal to 0, and the matrix of derivatives is degenerate. So then there exists some direction, which is some vector in which psi of u, the matrix of derivatives multiplied by this vector, say alpha, is equal to 0. So then in some direction, the function is proportional to epsilon squared when epsilon converges to 0. And therefore, the pre-image of our ball is proportional. Well, it is the pre-image of our ball is just some ellipsoid with one axis equal to square root of epsilon, the order epsilon. So it is just proportional to epsilon to the power 3 over 2 when epsilon goes to 0. So, but then this expectation will converge to infinity, but we already stated that it would converge to some finite limit. So then we obtain the contradiction. Further, let us define what is a random measure. So if we have some measurable space S with some sigma algebra on it, then a random function defined on some probability space omega is called a random measure if first for every fixed A, for every fixed set A from S, A alpha is measurable as a function of omega, and for all for any fixed omega, alpha is measured in S. This countably additive and equals 0. The empty set. Yes. Further, let us define what the sheet operator is, and let us define what is the stationary random measure. So the random measure on RD is stationary if it is just well, if its distribution does not change under any shift in space where R is from RD. Further, we can prove that gamma of psi is stationary sign random measure on R2 and borrow sigma algebra on R2. So it is signed and it takes only integer values and signed because well, it can take negative values too. And then further, let us consider standard theorem, the Rice's formula for higher order moments of NU. But well, said we can't use just this Rice formula since well, in our case, yes, here in the general case, J of t is beyond some set B, and psi of J is equal to some U. But we take well, simpler case, partial case where we just J is just greater than 0 and psi is just equal to 0. But we cannot apply it directly. Well, since well, in our case, we have F number F. Yes, so it will be just well, F term determinant of number F. So they want well, they will not be linearly independent. So this theorem cannot be well applied directly. Yes, so in conclusion, what we did is that using Kuznetsov methods developed by Kuznetsov, we found the formulas for the expectation and the second moment of the winning number of our Gaussian random field Xi on the smooth boundary of some constant B in R2. Also, the obtained winning number has the properties of signed stationary random measure on R2 with borrow sigma algebra. bits of other, let us see there is some literature. So here we have just some publication on the notes and a paper by Pittman Jordan about planar Brownian motion. And then we have books about random polymers and also the paper by Cousins of 2015 that I was talking about. So thank you, that's all, I think.
Okay. Thank you for the interesting talk. Maybe somebody have questions or comments, please.
I have a question. So, how much obtained results depend on the special form of the covariance function?
Covariance function? I mean, I didn't prove it like completely, but I think that for any covariance function from Schwarz space, they will hold. It is the formula for distribution, for dispersion, for the moments. It will hold for any Gaussian field with covariance function from Schwarz space.
Okay, so you need some smoothness, yes, and
Yes.
asymptotic behavior.
Not only. I think that at least in the knot model, again, can you show us slide number 5, I think, about the properties of the random knot, which is obtained as an image of the smooth curve and the okay, let's just 2 slides further. Next and next. Oh, stop. So we have here the theorem 2, where we just say that the obtained knot can have arbitrary topological type with positive probability. And to ensure this, we need some statements about the support of the distribution of the knot coordinate. And of course, this distribution is Gaussian measure, but it can be concentrated on the proper linear subspace of the space of periodic functions. In those cases, we cannot say that this theorem 2 will hold. So the idea of the proof was that the covariance has the Fourier transform, which is totally not equal to 0.
Mm-hmm.
This was the idea. So we need something else, but of course for the windings we don't need this additional property. But this was my question to Gennadii and comment. We need the highest moments, because this highest moments is nothing else than the distribution of the number of upcrossings for the obtained node. So if we will have this the estimation of expectation of the highest moments, we can conclude, due to the rapid decreasing of the covariance function of the initial random field, that when we move the circle, our we will have some like ergodic theory, and we will see what is typical knot. So this is the idea why we need highest moments. I think that Gennadii will get it. And then we can just have some estimations and say the typical knot is of such complexity or something else. Okay, maybe some other questions or comments, please.
Yes, I would like to ask about the Winding number. You considered generally the case of R2, two-dimensional space. But what about the connection with physics? I know the Winding number, for example, in deep brain theory, and Winding number is very useful topological invariant connected with some particle physics observables. So maybe you can say something about this field or something original connected with physics.
Maybe I will answer. So, first of all, Gennady told that the winding number of the projection is related to number of approachings, to number of those bridges. You are absolutely right that the number of bridges, which is actually some reformulation of the three-dimensional winding number, is closely connected to the energy of the knot. And we have the estimations, for example, that Möbius energy of the knot give us the upper estimation of his complexity. So when we have the moment of the winding number, we can say something about the Möbius energy of this knot. So we can say something about his physical characteristics. Of course, despite of this topological characteristic for polymer model, we have some other very well known in physics characteristics, which looks like very simple from the first point of view. For example, the radius of gyration. This looks like the radius of the sphere which contain our knot, of course, minimal radius of the sphere which contains our knot. So we also hope to be able to calculate such kind of characteristics because they are also related to topology of the knot. Why? Because we can control the second derivative of our random curve. It is due Georgi equation about the how smooth is the covariance function. We can control the model of continuity not only of the random field but its derivatives too. So we can control that there are a lot of small how to say small parasitary knots on our large knot. And due to this, we just hope to calculate further in future a lot of physical characteristics.
Okay, thank you very much.
You're welcome. Okay. By the way, also I want to mention our work with Katerina Glinina and Su Liu from Jilin University, which is placed already in Mass Archive, where we discuss the winding number in 3 dimensions for equation with interaction. And we relate this winding number with the energy of the vector field. It is a well-known theorem about the energy of the vector field in 3 dimensions, which says that spirality of the flow generated by the field give us the estimation from below for the energy, total energy of the vector field. So we did this for special case of equation with interaction. If it is interesting, you can find it in Max Archive. Okay, so if there are no any other questions, Then, Gennady, thank you again for your talk. And maybe we know who is the further speaker for the next week.
Yes, it will be Alexander Weiss.
Okay, good. So for today, we finish our job. Thanks, everybody, and see you next week. Bye.
Yeah,
Thank
bye.
you.
Bye.
Bye.
Bye.